Just a quick few words on the exams. If you hadn't noticed, you should. They're back. Through the grade book, what I did is I scanned them in and uploaded them to the Canvas gradebook, so you should be able to see those. Let me know if something didn't come out. I do have the paper versions, but right now they're at home. Eventually they'll be in my office. And I just thought this ends up being the best way to get it back. Usually I'll hand them back and about half of you will get them, and then the other half never do, but you want them and stuff, so let me know, though, again, if it didn't come through good or whatever, but I'd be happy to discuss any of the questions with y'all. It's a good way to study for and prepare for the final as we go forward. Let me disconnect from this. However, and again, the overall results in this class, we had almost a 70% average without any of the zeros, which are people that missed the exam or didn't take them, which is not bad, and our median's 72. I'd like to see an average about 80, and I'll bet you if we keep going and learning, maybe by the final we can get there. Or maybe 90. I wouldn't mind a 90% average. It's possible. So just keep, wherever you were, there were some 100%, there were some, a number in the 90s. But again, it's all about where you're at personally and how you're doing. And again, think about what you could do differently that might have impacted this. Some of you I know are just, you're doing everything you can, but just kind of keep going, and hopefully as we're going into this newer material, the older stuff's starting to make more sense. And again, that will be incorporated into how you do on the final, because there'll be similar type questions on there. I'll look at that, and if there's an improvement from there, I can take the improved version. I don't average, but I take the improved because you know more now. Okay, so that's kind of what we're looking at, is once you get to the final, we'll get you there. Just that, there is no, we can have up to 1% extra credit. That's not going to make a difference really all that much for any particular one. There are no retake tests allowed. Those are department policies that, whether I agree with them or not, I'm not going to breach them because that's the way it is. So anyway, keep pushing forward. And the main thing is if you got behind previously and we're kind of crunched at the end, that sometimes happens, jump to the forward stuff. Don't worry about the past so much, because the stuff from test 1 won't directly be on there. Yes, you'll need to know how to take a derivative and stuff, but there won't be anything on limits in test 2. So just kind of keep up with where we're going, and that's typically what I see when I teach this class, is test 2 is generally much better than test 1 overall, because we start picking up. Okay. Oops, before I go here, let's go back. Update where we're at. So notice I've got 12.1 and 12.2 split into 2 different days. So we'll just do the 12.1 looking at maximum, minimum. Usually we take these, we do these in 1 day because in the past 12.6 was a required section that was also on the test. Since it's not on the test, I'm going to make that extra credit. So we won't deal with it directly. It'll be available all the way till the end of the course. If you get a little bit ahead here, there will be a module for 12.6 with a recorded lecture if you want to look at it and give it a try. I may talk about it if we get a little chance, but it'll also be available later in the semester as well. So This is going to give us a little bit of room. So we got this week, next Monday is fall break, so we all get a little break in the routine. So we got 3 more weeks, 3 full weeks before the next exam, again, just to get going. And the good news is we are pretty much done with the skills part of what we've been doing. Everything else now is going to be going back over what we've learned and applying it. Doesn't mean it's not necessarily going to be a piece of cake, but at least we'll get a chance to come back and use those skills and then do a little bit of problem solving. All right. Let's go here. So this application is on maxima, and minima, maximum values and minimum values. Again, business applications, we like to maximize profit. We like to minimize cost. Okay, so those are 2 applications that we're going to look at. Just in general, I think I've got here. Oh, let me back up a minute. Oh, there it is. They took away my colors. So this will be in the slides that we'll sort of do, but if we're at this point here, thinking of this as a graph, what would the slope of the tangent line be at this point? 0. That's right. No, you're right. It's 0. The slope is 0. It's a horizontal line. It's increasing until it gets there, that it's flat, and then it's going to be decreasing on the other side. So, and the other place we get 0 slopes of the tangent line are at minimums. So here's the thing. Primarily what this section, these next 2 sections are about, is finding a derivative, setting it equal to 0, because at that place we're going to get either a maximum or a minimum. Now when we solve for that x value, we get the location of the minimum or maximum. It doesn't tell us whether it is a minimum or maximum, though. There's another section we'll do that will help us figure out whether it's minimum or maximum. But it does tell us the location of what we'll call it a critical point, because that's what the book calls it. And then we're going to test it. We'll get its actual y value from the original function, right? So the derivative function, we use that, we set that equal to 0. Where it's equal to 0, that's going to give us a minimum or a maximum. We go back to the original function, not the derivative, plug that in, and that will give us the value, and we compare it to the other values to see whether it's a high value or whether it's a low value. Okay. Do you see on this graph any other places other than the places where the derivatives would be 0 that could be minimums or maximums? There's 2 of them. Where are they? Where are the other places that could be minimums or maximums? At the ends, right. Because again, we can't take a derivative there because it's a point. If we were, it wouldn't necessarily be 0, but the value itself at the endpoints, like this one, you can see it is the lowest of the lows. It's actually the most minimum. And this one over here, this endpoint, is the highest of the whole graph. So it's actually what we'd call an absolute maximum. Okay. So we'll just put this in here, and then we'll use some math. I just call it an absolute max. Here's an absolute minimum. And then in between, we call these all relative. Yes, sir.
Would there not be two more on top of that, like maybe the bottom of that, like?
Yes, yeah. So then there's a place here again, but that's where derivative is equal to 0, and so we got two others exactly. We may be asked to find all of the minimum maximums, so we would do that. Notice you can do this by, if you're given a function, you can do it by graphing it and just looking at it. Okay, so we'll use that as an option, but we can also get it by finding the derivative, and sometimes that's what we have. So two big terms we get: relative minimum maximum, absolute minimum maximum. Absolute is there's only going to be one absolute maximum, because that means the biggest of the big. One absolute minimum, that means the smallest of the small. And then, but relative just means that in its neighborhood, if you're close by there, that's the biggest or the smallest. Like when I go to Thailand, they think I'm a basketball player. He says, no, I'm back in the US, I'm kind of short. Not anywhere. In fact, I'm not very good at basketball at all. I always foul out because I compensate that way. Okay, so sometimes, but in certain places I go, yeah, I'm pretty tall. Certain place I go, I'm pretty short. So it just depends, right, where we're at. So that's the relative minimum maximum. Okay, so let's go ahead and get into this. They also use the term relative extrema. So extrema just means it's a minimum or a maximum, but it's an inclusive word to say both of those concepts. And again, we use it in business because we're trying to maximize something: profit, revenue, production, get our workers to work as hard as, squeeze every little bit out of them, or happiness. Bhutan is a nation I've always wanted to visit. They measure national happiness, so they're trying to maximize their happiness. What a concept, huh? Okay, so a relative maximum is, just think of it, it's, on a graph, it's going to be the top of a mountain. So something like this. We can get a sharp point like that with a absolute value function, gives us stuff like that. We can't take a derivative at that point, but it would generate a maximum, a relative maximum for its area. And again, they might not be the largest value overall, but they're the largest for its region. So an example might be sales for the maximum sales for a given month. Month of September, the report comes in. On the 15th, we maximize our sales. Okay, that's a local or a relative maximum. It might not be the biggest for the whole year, but for September, that was the highest days of sales. Okay, so that's where the idea of a relative maximum comes in, and we contrast that with something called the absolute maximum. So then we'd be looking like maybe what is our highest days of sale the whole year, and that would be the highest of the high. Okay. You could also think of an absolute maximum as a relative maximum, right? Because it's in its neighborhood, it's going to be the biggest, it's going to be the highest peak there as well. But it's also, if you've got all the relative maximums listed out, the absolute one's going to be the biggest. That's all. Same things happen with minimums. And again, sometimes we like to minimize things. We want to minimize errors on the production line. We want to minimize rejected parts or something. We want to minimize the cost. And so, again, we think about a relative minimum is just in some local area that we're talking about, that's the lowest point. And there's also this concept of an absolute, which would mean there's one that's the smallest, the lowest overall. Okay. Two concepts, the way we talk about things. When they are talking about the location of an extrema, the location of a maximum, or location, where is it? That's always an x value. That's its location. When they ask about the value of the minimum, value of the maximum, that is the y value of the point. Because remember, every coordinate has an x and a y. Well, at least on the coordinate plane we're using, there's an x coordinate and a y coordinate. X gives us where it's at. The y value gives us what it's at, the value. Okay, so we'll use those two concepts as we go through. And just be careful, because a lot of times when the homework asks for the answer, if they're asking where is the minimum, they're not asking for the y value, they're asking for the x value. When they ask how much, those type of questions, you want the y value. Okay. You'll see, we'll get good practice at listing both of them. So here's a figure, and again, they've got one of these pointy things, which generally happens when you've got an absolute value function of some sort. You can't take the derivative here. We won't see too many of them, but we'll talk about it. They've got a special name for that kind of a extrema right here. We can see a relative max here, a relative max there, a relative minimum there, and then remember endpoints. If we're going to just look at, this year's sales or whatever, the endpoints might be the place where we have a minimum or a maximum. Might not be, but also might be. So there's basically three main areas we have to look at. We're going to look at primarily two of them: endpoints and places where the derivative equals 0. And then there's this third one that's kind of rare, but it can happen. That's places where the derivative is undefined. That could be a thing. But again, if we can if we're given a function and we graph it, we could just see where you can look. You can see, oh, that's high, that's a maximum. That's low, that's a minimum. Okay. So they define the points here. And again, what are they giving us down here? Are these values or are these locations? They're locations. Good. Because they're the x values. If we were looking up here, maybe one there. Looks like there's one down there. Maybe one up here. These ones, are those locations or values? They're values because they're on the y. So the values are over here. The locations are the x values. Okay. And again, a lot of reading that I'm not going to read through all of this, but just saying that we have a relative extrema when they'll define it with, basically if you look to the left and you look to the right and everything is either less than it is, then you've got a relative maximum. If you look to the left and look to the right and everything is higher than it is, then you're down in the bottom of a valley, you're a minimum. Okay. And then once we get all the values, we look for the biggest one, and that's going to be our absolute maximum. We look for the littlest one, it's going to be our absolute minimum. Okay. And again, they start mathematically talking about the neighborhood. So they found the point of concern, which is R, and they subtract H and they add H, so they're looking basically in a little neighborhood area. They're looking to the left, looking to the right, and R happens to be, this location of R happens to have the highest Y value. Okay, so this would be a relative maximum at R. Relative maximum at R, because as we look to the left, look to the right, the values are smaller. And you could do that with algebra. You could do it with a graphing calculator. We're just looking back and forth. But we could also do it with, we're going to see with calculus, we can take its derivative and find where it's equal to 0. So it can be done without the graph, but the graph is always very helpful. And so they give us this definition. We're going to work through some examples, but if you can see on the graph, that's basically what it is. It's a high point. That's a maximum. On the graph, it's a low point is a minimum. Okay. Again, but they use this notation just saying, you know, if we're around some point R, whatever it is, go to the left, go to the right, as long as all the y values are either larger or smaller, we have a minimum or a maximum. So let's look through some examples. So at point P and point R, we have what we call relative maximums. And again, we could find those because the slopes are going to be 0. But we can see those are relative high points. Just to jump the gun a little bit, what's happening here at point B? An absolute maximum. Which is kind of, you'll see in the slides, they'll say that if it's, the endpoints cannot be relative minimums or maximums, but then another slide shows one as being that. So absolute, yes, we're looking where's the highest, and that's what we see happening at B. And then we're looking here, actually it looks like we're going to get an absolute minimum at S, because it appears to be about the lowest, about down there. So absolute minimum and absolute maximum. And again, just more mathematical things, but just like what you would think, we've got a maximum if at that point that y value is bigger than every other y value. That's what it's saying, the greater that it's greater than everything around it. Not only everything around it, everything that exists, right? Absolute. Absolute minimum will be that case if every other function value, every other y value is smaller. Sorry, it's smaller than every other y value, right? Every other y value is bigger than it is. That's a minimum. Okay. So again, if you're a math major, all this stuff is very important for definitions and everything. Business majors, I see the graph, I get it, right? It's the bottom of the graph or it's the top of the graph. So that's all that's saying. We'll get into a couple examples here. So again, we did jump the gun, but absolute value, absolute minimums and maximums are right here. The lowest of the low, the highest of the high. Okay, and again, just remember those endpoints. And I only emphasize that because I would forget them. I would do all the calculus stuff and then I'd forget about those endpoints. So when I do them now, I'll try to do those first because they're easy to forget about because you get so caught up in everything else. Okay, so here's an example. We've got a function and we've actually got the expression x squared plus 1. We can see from the graph there's a minimum here, and we could also take the derivative, right? The derivative of x squared is going to be 2x. Derivative of 1 is 0. And if we take 2x and we set it equal to 0, we solve for x, divide by 2, divide by 2, we get that x equals 0. So we get the location of a minimum or maximum. Again, if we just have the function, we don't necessarily know, but by looking at the graph, we could say, oh yeah, x equals 0, there it is. Where do we get the y value of sometimes I misspeak myself. The minimum, it's an absolute minimum, right? Where do we get this y value? We take the location of the minimum, and where do we plug it into? we go back to the original function, not the derivative function, right? We put in the derivative, we just get 0. So we find that f of 0 equals 0 squared plus 1. F of 0 equals 1. So it's got a y value of 1. That's an absolute, so our absolute minimum value is 1, and it occurs at the location x equals 0. Okay. And we can see it on the graph, but in this case we could also use the calculus to verify it, that that's the place where the derivative equals 0. So the tangent line would be horizontal there, indicating a minimum. There's no endpoints on this one. That's because they don't limit it. It's just the whole function. So if there are no endpoints, this is going to be it. Are there any maximum points? No, because it keeps going. And again, we don't directly talk about limits, but where do these arrows go? They go up to infinity. And so infinity is not a number, and so we can't, because no matter where you say it, you could go higher, right? So there is actually no absolute maximums in this case. Okay, just that minimum that was found with the calculus. Okay, so here's talking about what I did before, is as we talk about it. So when they say at, they're talking about the x. And when they're talking about the value of, that's where they're talking about y. Okay. So the minimum's value comes from the y value. We use the original function, full function. The location of the minimum or maximum, oftentimes we use the derivative where the derivative equals 0. Okay. Okay. Now this is giving us an example. There's always, if there is an absolute maximum, there's just one. However, it could occur in the two places. They would just be the same thing, right? So like here, the value is the same, right? It has, so we would say it actually only has one maximum value, which is whatever that is, that y value, but it occurs at two different x places. Those two x places are the same. Okay, so it's two mountains exactly the same height. That can happen, but you cannot have two absolute maximums, right? Because one would be bigger than the other, is the way you think about it. The value, you can only have one. You can have a tie, but you can only have one maximum. Okay. Now we'll get into locating them. We've kind of been doing that a little bit. Visually, we can do this, locating them right on the graph. And this is what I mean. We're going to get some other names for them. The ones that I talked about, if we are limited in the domain, if they have some endpoints, the endpoints are possibilities for maximums or minimums. Okay, because typically they are relatively going to be a maximum or minimum, but that's it. Then they use this term stationary point for wherever the derivative equals 0. And why stationary? Well, think about it. If their derivative is equal to 0, at that point, the amount of change is 0, right? The rate of change is 0 at that point. So it's, in that sense, it's stationary. Doesn't mean that the function's going to, won't change. It'll go and change, but so that stationary point. And then this one that we don't use all that often, singular points, because it needs a really specific type of function. But it can, it's a place where we can't take a derivative because the derivative is undefined at that point. So they always throw a few of those in there. We'll take a look.
Why is it undefined at that point? What would you say?
No, the reason is if you go to a sharp point, how many different tangent lines could you draw? You could actually draw an infinite number of different tangent lines through that kind of a point. And so that's why the derivative doesn't exist there. Okay. Again, it's a very specialized one, which if you want to, you could just forget about it for now, and then when we face it once or twice, we'll deal with it, but we'll focus on the other ones. So we're going to focus on what we call stationary points. And again, think about it. If the derivative is 0, that means that the rate of change is 0, so that's why it's not moving at that point, sort of, stationary points. In the homework, again, this comes from the textbook. If I don't use these words, when you go into the homework and it says find the stationary points, you go, what is that? So I use them. This is the first book I've seen this use of the word stationary points, and but so we'll use it. So what we're going to do, again, we're going to look at a few examples. I'm going to check the endpoints first because I tend to forget those. Then I will look for stationary points by taking the derivative and setting it equal to 0. And then I will graph it if I can, or sometimes we start with a graph. Doesn't hurt to start with a graph, but if we connect all those three things, the visual of the graph with sort of the analytics of the function, then we can understand this pretty good. We're going to skip over the singular points right now. I believe there's one in the homework. We'll look it up and we'll do that together. And what we do is when we find these places, we call them critical points. So here's all these words. Stationary points are where the derivative equals 0. We also call them critical points. Every other book I've used, they just call them critical points. But this one throws in this extra vocabulary. So we'll use it because they also use it in the homework. And then endpoints are always something that you have to come back and take a look at because, again, endpoints, technically we can't take their derivative there because to take a derivative you need to go, remember it comes from limit, so you have to go to the left and the right. The endpoint is missing either a right or a left side. But we just plug it into the function and we're good. Okay. So here we've got this example they've showed us. They're calling this one a relative minimum because in its neighborhood it's the smallest point, it's the lowest point. It's not the absolute. Here's the absolute minimum. Here's an absolute maximum. And the rest of these are all relative, two relative maximums, a relative minimum. And they've labeled them as stationary or not. And typically what we do is we find where all these locations are. We plug all these x values into the original function to get the y values, and then we line them up from smallest to largest and figure out which ones are the minimums, which ones are the maximums.
So there's no endpoints in the tablets?
It depends. There could be. They just didn't give us any. Sometimes they will have endpoints, but that's sort of an imposed thing. This function actually probably continues on, but they, for whatever reason, they're only interested going to here to there.
So then if it was an open interval,
Right. So if they give you open intervals, function continues, there's no endpoints, you don't have to worry about them. Okay. Okay. So stationary points where the derivative is 0. Singular points, again, we're not going to worry too much. That's where the derivative is undefined, and you'll see there's just a couple places that happens, and then endpoints. So we're going to focus on stationary points and endpoints. Okay. So here's actually it's right out of the homework. They ask you to find the values, and so. And they give you a couple, there's a couple in the homework that are like this. They just give you a graph. They don't give you the formula. They don't give you anything else. So this is all just saying, okay, that looks like a maximum. That looks like a minimum. and here's an endpoint, and here's an endpoint. And so maybe going from left to right, we can say we've got function value at -9, and what would the y value be there? 0. This one at f of -3. And notice I'm using the original function, not talking about the derivatives here. I can see that that's a maximum, and it would have a value of 6. And then here's another one, f of 3. It's going to have a value of -3. And then f of 9, which is an endpoint, it's going to have a y value of +3. So I'm just going to label this EP for endpoint, EP for endpoint. And then what kind of points are these two in the middle? They're that, but they're all stationary. Good. It took me, I've had to teach this like 3 semesters before those vocabulary start sticking, but those are also stationary points. And if you wanted to, you could think a tangent line through these would be horizontal. Tangent line through this one, yeah, horizontal. Okay, so these are stationary points. So I'll put S. And then how did you know that those two are absolute minimums or maximums? You see it. Does anyone have another way they could tell that those are places of absolute minimums and maximums? What does this tell you? It's a max. Yeah, there's not because we looked for all the high points and the low points. 6, that's got to be the highest of the high, right? There's none of these other y values is bigger than 6. Okay, so this is going to be an absolute max. And when you look at this number, -3, you compare all the y values, it's the lowest of the low, right? There is no number lower than it. And again, you also could see it. So there's those two ways of doing things. Okay. Visually seeing it on the graph, and then also analytically saying, hey, that's the lowest number. There's no number lower, so that's got to be an absolute minimum, making this one a relative minimum, min, and this one over here a relative max. And we go back and forth. Some place in the book it says that endpoints can't be relative mins or max. Another place in the book it calls them relative mins and max. For their neighborhood, that's a minimum, right? If you look around the area, what they're saying is is if you're real technical that it doesn't have anything to the left. So, but let's go ahead and call it. We had a big blow up on one of the exam questions. It was a true false, and so it's a technical thing, but we could go ahead and call them relative minimums and maximums. So far so good? So you've got about 3 or 4 of these where they just give you the graph. You're just going to pick the points off of it. You're going to list them sort of in order, and you can either use the numbers or the visual on the graph to tell minimums and maximums. Okay. Also from the homework, there's going to be a few of these that they'll give you. They will give you an equation, a function, and they will give you, or not give you, they'll give you an open interval, but in this case they're giving us a closed interval so we have some endpoints. Okay. So find the exact location of all the relative and absolute extrema of the function. So I'm going to walk through this one, and we're going to do it analytically, and then we'll look at the graph and see that it all's there. Again, when you're doing these, you could start by looking at the graph first, however you want to do it. Maybe on one of them, do it that way, but try to do them both ways. So what did I say I was going to look at first? Because I always forget. Endpoints, right? So I want to find f of -2 And notice we don't have any we don't do any calculus for this. This is all algebra. We just plug it in, and I want to find the other endpoint, f of 2. And again, I just plug in the values. And this is where, you could just also plug it into your graphing calculator, because then you could see the graph, and then you just use the table to look it up. But I'll do it this way. Negative 2 to the third is negative 8. Negative 8 times 4 is negative 8 times 4 is negative 32. Negative 12 times negative 2 is positive 24 plus 6. 24 plus 6 is 30. A negative, so this should be negative 2. Is that right? Got to check me, because I do things in my head and I get lost. But someone check me on that. So we've got, I don't know why they did that to me. Okay, so this is a y value. That's a, again, that's going to tell us whether we have a maximum or minimum for these. This over here, these are x values, these are locations, these are places it happens. So what are we missing? We're missing any place the derivative equals 0. So that's how we would go about this. Oh wait, I haven't finished this one yet. I should do this one. 4, 2 to the third minus 12 times 2 plus 6. 2 to the third is 8. 8 times 4 is 32. That's positive. Negative 12 times 2 is negative 24. And plus 6. Let's see. 6 plus 32 is 38. Minus 24 is 14. Did I get that one right? Okay, thank you. Always like some validation on the calculations. Okay, so now we're going to look for potential places where we have some minimums and maximums maybe between these two. So we're going to take the derivative of g of x. Derivative, 3 comes down, 3 times 4 is 12. Subtract 1 from the exponent. This is x squared. We good so far? The first derivative. Derivative of negative 12x is going to be negative 12. The derivative of x is 1. We're done. And then the derivative of 6 is 0. So this is our derivative. We're going to set this equal to 0. And let's see. We could factor out, again, you could also just take a graphing calculator, find where it crosses the x-axis, but let's do this a little bit by hand. Could we factor a 12 out of both of these?
Yes.
Yes, we could. So we do that. And then divide both sides by 12. 0 divided by 12 is still 0. So then we get x squared minus 1 equals 0. Add 1 to both sides. We get x squared equals 1. And then we could take the square root of both sides. And that gives us that x equals, we have to remember this gives us a plus or minus 1. When you take a square root, you get both a positive and a negative. Okay. That's why I also like doing it with a graph. So at this point, I'm going to do that because how many of you don't feel very good about factoring? It's okay, you can raise your, I'm raising my hand because I don't. I've never really liked factoring. I always liked using the graphing tools. I got better at it because they pay me to do it, so not because I, yes.
So you take like a square root there. Does that mean there's going to be two extrema at -1, -2, and then 1, -2?
Yes, sort of, yeah. At -1 and +1, there will be extremas. Yeah, the endpoints, we've already captured those, and then we'll get stationary ones. And that's why I'm going to go to the graph at about this point, just to for any of us that have maybe gotten a little lost, we'll look at the graph and then maybe it'll help us come back. I'll use a TI-84 because that's the one you can use on test, right? Or if you've got a Casio, that's fine. So we're going to put in the actual original function, which is 4x to the third power, and what, minus 12x plus 6. I'm going to, one little trick on the window, since we're only going from -2 to +2, I'm just going to look from -2 to +2 for my x's. That's what's going to hold the window down so I don't have to look at any extraneous stuff. My y max and min, I think we'll, let's just go maybe -15 to 15. I think that'll do it. And then we'll graph it. And that's what we're seeing, right? We saw endpoints. We got this one, and we got that one already. We see here at -1, we've got a maximum. Here at +1, we've got a minimum. The cool thing about using the graphing calculator, again, without doing any calculus, right? But if you want to do some calculus, you go second calc. You could actually take the derivative. That's dy dx. Let's do this. We're going to take the derivative at -1 and watch what we get. We get a derivative that is basically 0, e to the -6 power. But it also gives us the y value. Okay. The other thing we can do is we can go to the table. So this saves us from having to do all this arithmetic where we might make an error, right? That's where I usually will make an error. But if I'm careful and plug it into the graphing calculator correctly, I come to the table. -2 has a value of a y value of -2, and we've got that here. Again, I could have saved myself some work there. And then we also know that at -1 there's 1, so it's 14. So I was able to get that value without having to plug -1 in and go through a bunch of arithmetic. And then +1 is -2. Okay, so we've got, let's see, go back to here. We found critical points at -1 and 1, and their value, I think this one was 14, and this one was -2. Okay, so that's what we go back. And again, we could have just started with the graph. That's fine, but we want, since this is a calculus class, we want to throw in some of the calculus. So if you want to start with the graph and find out where they're at, then take the derivative and then verify, oh yeah, at the derivative, these are the points where it's equal to 0. Make that connection for the content, but whichever way works better for you, right? Whichever way is going to make it work for you. And what I find, if I use the method that's easiest for me at first, I'll do it more often. If I take the hard one, I get tired and I don't do it again. But it's actually better if you'll take the easier approach for whatever one works best for you. So if it works best for you to graph it first, and I think it will, because you can actually see it, right? Do that, and then take the derivatives. So find the exact location of all relative and absolute maxima, extrema. So what do we know about these 2 points, or these two? -2, -2, 1, -2. What would you say about those? What kind of points are those? What kind of extrema are they? Are they maximums or are they minimums? They're minimums, right? And the only reason I know that is because the other one compared to is 14, and -2 is smaller than 14. And again, we looked at the graph. Those are the lowest points. So we have two points where that have the same absolute minimum, right? -2 is -2 is absolute minimum. In the homework, what they will ask you to do is list all 4 of these points. And then next to each of the point, you will say whether it is a relative minimum, a relative maximum, an absolute minimum, an absolute maximum. So you would list these 2 points, and incidentally, when you do the homework, they want you to list by smallest x value to largest x value. That's why I list them here from smallest x value to largest x value. And if you put your answers in that order, you'll be just good. If you put it in a different order, it'll mark it wrong because that's just how the checking system goes. Okay, so put in from smallest x to largest x. You put in the points, the x and the y, and then you identify, are they an absolute max, absolute min, relative max, relative min. Okay. So far, so good. Okay, so that's what these two, and then these two that are equal to 14, again, they have the same maximum value, and they are the absolute maximum for that interval that they gave us. And that's why I say when I look at the graph, come back to here, I squeezed in the x's to be on just that interval from -2 to 2 because I looked there, oh yeah, that's all that I'm focused on what I need. And I see that those 2 values are the endpoint here, and this one same, this minimum, same, and we're good. Okay. So you'll get a couple questions like that where they'll give you a function. There's one with an x squared, so you'll only have one to find. It's a parabola with some endpoints. There's a couple with e's. I think I've got one more example. But again, we would say these points here. Oops. Sorry. So -1, 14. And 2, 14, these both together form, these are both absolute maximums. And again, there's one absolute maximum value of 14, but it occurs at 2 places. Questions? Okay. And again, you could do this all without any calculus. Just go to your graphing calculator, look at the graph, look at the table of values, but then also remember to come back and take the derivative. All we're doing is those stationary points, the 2 in the middle, that's where the derivative equals 0. Okay. Here's another one. Find the exact location of all the relative and absolute extrema of this function on this interval. Okay. So again, I always like to start with the endpoints, because if I don't, I'll get doing the calculus and the graphing, and maybe I forget about them. So one endpoint, right, is f of -3. So I'm just going to plug it in, e to the -3 squared, so that's e to the 9th. So that's a point -3 e to the 9th. That's a pretty big number too, isn't it? I don't know, e to the 9th. But the thing is in the homework they'll ask for exact location. They want us to list it as e to the 9th. That's an exact number. If you put it in a calculator, you get a number that probably will blow out. It's so large, it probably turns it into scientific notation. Okay, So we could list that. Where's the other endpoint? F of 2. So again, we put in e squared to the second squared. That's e to the fourth. So the other point is 2 e to the fourth. Again, I'm going to, how do I find if, so those are the endpoints. How do I find if there are any stationary points? Derivative, right? Or I graph it and I visually see it, but I want to build up a little bit. So we'll graph it and you'll see there is actually a stationary point. So what's the derivative of ex squared? Whenever you have e to some power, what's always the first, what's the outside derivative? E to that power. You just copy it. That's the first part of the derivative. So the derivative of the outside is e to the x squared. Remember, it's weird because it's its own derivative, but that's the first part of the derivative. Then we have to use the chain rule. We're taking the derivative of the inside. Where is the inside of a function for an exponential? The exponent. So then we're going to take the derivative of the exponent, and the exponent's x squared. What's the derivative of x squared? 2x, right? And so I'm going to put that in front just because that's where they usually put it. That's the derivative of e to the x squared. So see, we keep going back to what we've been doing and re-emphasizing it. And that's how we learn by going forward. That's what I really want to encourage you to keep moving forward on this, because you'll pick up things from the past that you didn't understand as you move forward. Does that make sense? So that's its derivative. Where is this derivative equal to 0? Well, 2x e to the x squared. I set it equal to 0. I can separate this because I got two things that are multiplied, right? I've got 2x times e to the x squared. So if one of those is 0, right? If I'm multiplying two numbers and one number is 0, I will get 0, right? So this is a property we use a lot. So rather than trying to get everything to one side or solve for x, which you really can't do here, but we say, okay, what if 2x were equal to 0? Then the whole thing's equal to 0. What if e to the x squared were equal to 0? Well, this one I can do, divide both sides by 2. I get x equals 0. But does e to the x squared equal 0? Does that even have a solution? No. If you just kind of remember e to the x, it's got a horizontal asymptote at y equals 0. It gets close to it, but it never gets equal to it. So you could take a natural log of both sides, but if you do that, the natural log of 0, that's undefined. So that might be the way you say, okay, you can't do this one. This one doesn't yield anything. And this is about the time also where doing the graph comes up, there's only one place, so this other one must not matter. Okay, so this doesn't happen. And so what this did is it gave me a location where I have a stationary point, a place where the derivative equals 0. So now I come back to the original function and I plug in 0, and let's see what we get. Original function was e to the x squared, so that's e to the 0 squared. 0 squared is 0. What is e to the 0? Oh, you know it. Anything to the 0 power is 1. Oops, that's a big one. Didn't mean to go that far. Okay. And so, which one of these numbers is the biggest? I don't know what e to the 9th is, but it's certainly bigger than the other two, right? This is a max. It's an absolute max. Absolute. This also would be a relative max because it's an endpoint. What would this be? Let's think about it. I've got a graph at -3, I've got a maximum. At +2, I've got a maximum. And I've got a smaller number. I got y equal 1 in between them. So what does that mean it has to be? It must go down. It's got to be a minimum. And the thing is that between those 2 points, there is no other stationary point. It's not really undefined here. So let's take a look at the graph and see if that's what we see. So going from -3 to 2. So I would call this a absolute minimum. Just from, and this is all abstract, and then when we graph it, we're going to verify it and feel a lot better about it. Again, you might start with the graph first. That's fine. But then kind of come back and try this thing with the derivative. Because that's all we're doing this in today. There's no application problems. There is just sort of these skill-based problems. Oh, we're doing good on time. So I'm going to clear this. I'm going to put in e raised to the x squared power. And I'm going to go to my window, and I want it to go, the boundaries are -3 and 2. We saw that e to the 9th was like the y maximum. I'm going to show you, what is y to the 9th as a number? I don't know. So I'm going to put in e to the 9th. And I think we're okay. Oh, it's 8,103. Not that bad. So I'm going to now graph it. Wow, that was we can see it's way up there, right? But do we really see what's going on down here? Probably not. So I'm gonna, let's bring this down to maybe 50. So do we see a minimum here? And then it's going to go up here. We don't see the absolute maximum. Let me do one more thing. Let's make it 20 and -5. A little bit better, clearer. And then we could also go to our table. And we see when x is 0, we get 1, and we see the numbers on either side are going up, right? So also the table helps us see that that's a minimum because everything else is going up on it. Not using calculus, but calculus helped us to see that that was the place where the derivative equals 0.
So the endpoints can be absolutes, right?
Yes, yes, and often are, because that's where, the endpoints is where it starts. I also say it's okay, and there's books that will say it's okay to call the endpoints relative minimums or maximums too. This book is kind of double, it sometimes says you can't, but then it does it anyway. I think that was the last example. Let me just see. Yeah, and then we get into applications. We're going to wait for Wednesday to look at the application. So if you can work, I think there's maybe 9 or less homework problems just like this, graphs, some equations, find the endpoints, the y values of the endpoints, find your stationary points, figure out which one's the smallest, which one's the largest. That's all we're doing in this. And then on Wednesday, we'll make applications. We'll actually do some word problems.
Thank you, sir.
Thank you.